In this video, I'm going to explain why EigenLayer could be the fourth major paradigm in cryptoeconomic capital efficiency, with Bitcoin being the first paradigm, Ethereum the second, and rollups being the third. Blockchain security can be divided into two main categories. We have our cryptographic security and our cryptoeconomic security. Cryptographic security refers to the security that we get from our cryptographic primitives, our digital signatures, hash functions, zero-knowledge proofs, etc. And generally speaking, the security of these things is very good. For example, when you do an Ethereum or Bitcoin or Solana transaction, you're creating a little message telling that system what you want it to do for you. Maybe send Bitcoins on the Bitcoin network or swap tokens on Ethereum. And that message is then signed. You're signing that message using your private key along with a digital signature scheme like ECDSA, which is an elliptic curve scheme. And doing all of that work, creating this signature for your message, is very cheap. It's like less than a cent of electricity to run your laptop to create that signature. But the cost for an attacker to try and forge your signature would be immense. It's like all of the world's classical computers would have to work on that problem for thousands of years to brute force forge your signature and steal your tokens, right? So there's this tremendous asymmetry there. There's this tremendous defender's advantage that you have using this scheme. You're spending like a cent to create this signature, but the attacker would have to spend like billions and billions and billions of dollars to forge that signature. So this is a really good deal, right? And anytime we can solve a problem with pure cryptography and get this incredible deal, this like 1 cent to trillions of dollars asymmetry, we probably should do so. But not all problems can be solved with cryptography alone. For example, in these systems, in blockchains, we need to ensure that blocks are reliably produced into the future, that the chain history is not arbitrarily changed, that the blocks which are created prioritize the most economically high value transactions, etc. And these are not really objective mathematical things that we can assert with math or cryptography, right? You can't mathematically assert that some block producer in your pool is going to create a block at some point in the future because they're their own independent agent with free will. So in order to solve this wider set of problems, we need to introduce economic incentives to our cryptographic tools, and we get cryptoeconomics. And with cryptoeconomics, we can solve a larger set of problems. We can, we can't mathematically guarantee that a block producer will produce a block, but we can economically incentivize that to happen, and it will tend to happen. We can't guarantee that the chain will not be reorged in a proof of work system, for example, but we can economically disincentivize these big reorgs and it'll tend to work out. They will tend to not happen too often. And so with cryptoeconomics, we can solve a wider set of problems, and it's cryptoeconomics which has enabled this entire blockchain thing to happen. Pure cryptography alone was just not adequate. It's not sufficient to create these kinds of global decentralized money systems and world computers and so on. Now, the strength of our cryptoeconomic security is going to depend largely on how much capital is involved. The more capital involved, the stronger the economic incentives, the better. For example, in a proof of work system like Bitcoin, we want the mining industry to be very large in terms of capital investment. We want there to be a lot of capital sunk into this industry in terms of the mining facilities and the ASICs and all that stuff. And we also want a lot of capital to be spent running that hardware, so that what that means for an attacker who wants to gain a majority hash power is that they're going to have to spend a lot of money too. They're going to have to invest a bunch of capital, build out their facilities, acquire ASICs, and then spend a bunch of capital running their hardware, conducting their attack. And that's the whole defense against these attacks, is you just have this big capital investment, this big barrier to entry to gain majority hash power in terms of capital investment. And so it makes it expensive for an attacker to do their attack. It's not impossible, it's just expensive. And it's the same thing more or less with Ethereum in proof of stake. It's expensive for an attacker to conduct an attack because they're going to have to acquire a whole bunch of ETH to obtain, 1/3 of the staked ETH or 51% of the staked ETH. They're going to have to acquire a bunch of ETH, and then when they do their attack, they risk it being slashed. So they risk losing all of that money. So in either case, it's not impossible to do these kinds of attacks. It just becomes very expensive. So the magnitude of capital in our cryptoeconomic, security systems determines the strength of them and how hard they are to attack. So in summary, cryptography secures some of the more objective, kind of smaller components of our system. Cryptoeconomics secures some of these larger, more subjective components of the system. And then the total capital magnitude, the amount of capital involved in our cryptoeconomics, determines the strength of that cryptoeconomic security. Now, the next question we can ask is, how efficient are we being with that capital? Suppose we have a bunch of capital locked up in our system, we're achieving a certain amount of cryptoeconomic security. Okay, now what are we doing? What is the system that we're securing with that capital? What does it actually do? How much stuff can it do, right? Like, how efficient is that money being used? And so this brings us to these 4 paradigms of cryptoeconomic security, with EigenLayer being the 4th and most recent paradigm. The first paradigm here is Bitcoin, and here in my diagram, I'm attempting to represent the total cryptoeconomic security of the system as the volume of this green cube. So this is essentially the capital invested in the mining industry, and therefore the cryptoeconomic security of the system. And this cryptoeconomic security is securing, it's serving as the foundation for the Bitcoin product, which sits on top of it, which is the Bitcoin ledger. This is the end product that the users actually care about. So this ledger allows the users to hold Bitcoin and to send and receive it. And this ledger runs at 5 to 7 transactions per second. So all of this capital is enabling the functioning of a secure ledger that just allows send, receive, and it runs at 5 to 7 transactions per second. Now, shortly after Bitcoin was created and went live, there was the desire for more coins and more functionality. And the easiest way to accomplish that, of course, is just to create a new separate system, which is what Litecoin and Dogecoin were. So the problem, though, of course, here is that you're having to bootstrap your cryptoeconomic security from scratch, right? You're having to create a brand new mining industry, and in general, that mining industry is probably going to be a lot smaller. If your currency, if Litecoin is less popular than Bitcoin, the mining industry will probably be much smaller, and therefore you'll have less cryptoeconomic security. So if we're wanting to have thousands of currencies, which we clearly do, this is not an efficient way to do it, because you're going to be splitting that security across thousands of systems. So one way to try to reuse this capital and extend the efficiency of this cryptoeconomic security is to do something like merged mining, which is what Namecoin does, which is a way to allow Bitcoin miners to mine 2 different systems at once without splitting their hash power. But there's limitations to this approach. It's debatable whether you're really getting the security for your merge mine system that is implied by the hash power that it has. The incentives are not necessarily perfectly aligned, which I won't go into, but that is one approach that was tried and is used. Another approach is to add layers on top of this system, on top of the ledger in this case. And this is what was done with colored coins. So here we're marking individual Bitcoins with a color, so to speak, some metadata, which allows that fraction of a Bitcoin to represent some other asset, maybe some real world asset like a car or something like an NFT. And then you can use the Bitcoin ledger and you can send these fractions of Bitcoins around, these colored coins around, and that will represent a transfer of ownership of the car or NFT or whatever as well. And so that gives you sort of this NFT layer on top of Bitcoin. Another protocol was Mastercoin. And here we're extending the functionality even further. So with Mastercoin, you're embedding in your Bitcoin transactions, Mastercoin transactions. And there you can have actual discrete separate currencies. You can have like a proto Pepe, and you can do your Bitcoin transaction and embed in there a transfer for like 50 million Pepe from yourself to some other user. So now the Bitcoin blockchain is kind of being used to embed this like secondary protocol, these transactions for this other protocol inside of that chain. And this unlocks a certain amount of functionality, but what was realized by Vitalik, actually, who worked on both of these protocols, is that every time with Mastercoin, there was a need for kind of new functionality, like we want tokens, we want to do dexes, etc. The Mastercoin protocol would have to be upgraded with new transaction types. So there was this continual need to, every time you have a new use case, to come up with a new transaction type, and kind of like you would have this kind of never-ending array of these different transaction types for different kinds of actions that you might want to do. And what Vitalik realized is that you should really just have a programming language, right? If you have a general purpose Turing complete programming language, you can just allow people to write programs, smart contracts, that can do whatever you want. So you don't have to continually upgrade and make changes to the protocol. You just embed a language. People can write anything they can imagine, right? A general purpose language, a Turing complete language can, it can do anything that any language can do. So if you embed that into the system, you unlock this like infinite array of capability. And of course, this is what happened with Ethereum. So to quickly recap, in phase 1, in paradigm 1, we have Bitcoin, where our cryptoeconomic security is securing just a simple ledger that runs at 5 to 7 transactions per second. Then we increase our capital efficiency and we essentially reuse that cryptoeconomic security to run these extra layers on top of the ledger, which unlocks some additional functionality, but which are sort of hacked on and don't really unlock the full range of capability that we might want. And then in paradigm 2, we have Ethereum, where we kind of achieve the full realization of this idea, where we bake a general purpose programming language into the thing which is being secured by our cryptoeconomic security. And therefore, this cryptoeconomic security, this capital, is in a sense being used as maximally efficient as possible, because the range of things which it is allowing to happen on top of it, the range of things it's securing, is essentially infinite. It's anything you can write in code, anything you can program, this system which runs on top of that capital will execute securely. Now, the next thing that is done, paradigm 3, is that we have rollups. We expand the capacity of this system. We increase our capital efficiency again, except this time we're doing so in terms of allowing more operations per second essentially to happen. Because in paradigm 2 with Ethereum, we've achieved a general purpose programming language and it's Turing complete, and there's nothing beyond that. Like there's nothing beyond Turing completeness. The language can do anything any language can do. So you can't improve in that direction anymore. But at this point, the system has relatively low transactions per second, like 15 or 20 or whatever. And there's reasons you can't really expand beyond that, which I've talked about in other videos. But this next paradigm is with rollups, where you're now enabling like hundreds of Ethereums essentially to run on top of the main Ethereum. So this capital is now effectively securing not just one Ethereum, but like a whole expanding tree of these other Ethereums that run on top of the main Ethereum. And so this is a massive breakthrough in terms of capital efficiency. So with paradigm 3, with rollups, it seems that we've kind of maxed out our capital efficiency. We have our core system, which has full programmability, and then we're able to run hundreds or even thousands of these rollups, these additional systems on top of our core system. So this capital is securing effectively all of these things running on top of Ethereum. And so we have full programmability across hundreds of systems and an aggregate of like hundreds of thousands of theoretical transactions per second. So this should be kind of the end game for capital efficiency in a certain sense. But there's actually a little more that we can do, because I'm going to switch to a different version of this diagram. Because the rollup ecosystem, this rollup landscape, is actually a little more complicated than that. We have these other auxiliary functions that we need to support this ecosystem. So for example, we have sequencers. Each of these systems, each of these rollups, is its own chain, its own independent like Ethereum or Ethereum-like system. And so it has its own set of sequencers that have to sequence the transactions, which update these states. And that task involves a certain amount of power in a certain sense. Like these sequencers have the potential capability of censoring transactions, for example. Now, because of how rollups are designed, there's limited power that any entities have. When you're on a rollup, there's really not a whole lot of bad things that can happen, for example. If the sequencers become corrupt and censor your transactions, you can always safely exit the rollup, right? So there's never any real risk. You're not at risk of losing in this scenario. You're not at risk of losing any money or anything. But still, it's kind of not ideal if some big rollup can start censoring transactions, right? So in order to kind of align the incentives here and ensure these systems function properly, we need to have alignment of economic incentives, right? It's kind of the same problem. Like, we can't cryptographically guarantee that these sequencers will be ethical, but if we align incentives and create the proper cryptoeconomic systems, we can provide we can have penalties for censorship, etc. But to do that, we need to bootstrap some cryptoeconomic security again, right? And this doesn't have to be like hundreds of billions of dollars like with the core system. It's probably fine for it to be a lot less than that. But we do need to bootstrap our security, right? So this presents sort of an additional problem that we can potentially solve. And it's not just sequencers, by the way. There's other functions and systems that we need to support a healthy rollup ecosystem. For example, we also have the whole data availability thing, where these rollups need to post data to some data availability system. And we may want some of these rollups to be able to run extremely cheaply and not post their data to Ethereum, to the 4844 blob system. We may instead want them to be able to post data to super cheap data availability engines. And there again, we have a system which is outside of Ethereum, which is not secured by this cryptoeconomic security. And so for a brand new data availability system, it would have to bootstrap its own cryptoeconomic security. And this is where EigenLayer enters, because without EigenLayer, as I've said, we have to bootstrap the cryptoeconomic security of these independent systems, including the data availability, etc. But EigenLayer is this new way to reuse and increase the capital efficiency of our cryptoeconomic security, our capital that's securing the system. And we're able to reuse that capital to secure this huge range of additional systems, including data availability services and the sequencers, etc. So now this cryptoeconomic capital that is being used to secure Ethereum and the stuff that runs on top of it can also be used to secure things which run outside of Ethereum, right? These systems which are completely independent and different. And the total range of systems which we might be securing there is vast. Like, there's no real limit on it. And this is some of the existing AVSs, which are these EigenLayer services, these separate systems which are secured through EigenLayer. And we have all kinds of stuff. We have data availability services. We have, frankly, a bunch of stuff which I don't even know what it is, which maybe I'll research at some point. But there's like Oracle systems, there's ZK bridging stuff, there's interop, there's hyperlane interoperability. There's all these things which may, make for a more functional and strong rollup ecosystem, and which may do entirely separate things which have nothing to do with rollups. Like, I'll explain how EigenLayer works in a more concrete sense in a minute, but there's really no limit that I can think of to what EigenLayer can secure, right? These nodes, which are already tasked with securing Ethereum, and they have their capital locked up, they have their ETH locked up, they're just being asked to run, or they're opting in to running some other software on their computers, on their machines, which is doing some other task. And they simply there's some rules that they have to follow. They have to be honest in their operations of these systems, or they risk being slashed. So the capital is just being reused. And as I said, there's really no limit that I can think of to the possible systems that we could secure in this manner. And by the way, this whole EigenLayer thing is potentially extremely lucrative for the Ethereum stakers, because now as a staker, you get your, your rewards from Ethereum for securing the Ethereum system. And then you can potentially also opt into EigenLayer and receive additional rewards for doing any number of extra tasks, right? One node could be running this AVS, could be running as an operator in this AVS, as well as this one, and sequencing. And they can now do a whole bunch of extra tasks, and they're putting their capital on the line. So they're taking a risk, no doubt about that. But they are also going to receive rewards for doing that work. So maybe they're getting, 2 or 3% from Ethereum for staking their ETH. And they might also be getting like 5 or 10% from some other AVS, one of these systems, because that system is going to want to attract, stakers, restakers. And so it's probably going to offer a high return. It's probably going to be printing tokens and paying the restakers with those tokens. So there could be all kinds of additional rewards that are accruing to these restakers through these other systems. And on net, their total return on their capital, that their 32 ETH or whatever, could be in aggregate like 20% or something. And this is great in a sense, but it also introduces some real complexity and challenges in terms of when you're designing like the issuance curves for Ethereum. You now have this whole realm of these EigenLayer AVS services, which are also paying your stakers, but in a way that you're not really aware of. Like they're completely outside of your system and outside of your control, and they're now paying your stakers, which it complicates the incentives a lot. And I won't go too much into that, but there's whole long threads on ETH research about how to the potential downsides to this and how to mitigate it, et cetera, et cetera. But that's another topic. Now, I'll now give a quick explanation of how EigenLayer actually works, because I think it provides a lot of clarity to actually understand how this works on like a smart contract level at a decently high level. And then I'll do a quick summary of this whole thing, and then I'll wrap it up. So the way that Ethereum proof of stake works is that we have a consensus layer now and an execution layer, and they're distinct in certain ways. So if you want to become an Ethereum staker, what you do is you have some ETH on the execution layer, like a regular Ethereum account, and you deposit that ETH to a special contract, which is the staking contract, right? So you send some ETH to this contract, and it kind of like enters you into a queue, and then that ETH sits in the consensus layer in this sort of different place, and you become an Ethereum staker. Now, when you do that, you also have to set a withdrawal address, right? So you enter your 32 ETH from whatever address, and you set your withdrawal address. Now, under normal conditions, the withdrawal address that you set might be the same address that you entered from, right? I send 32 ETH from this account, and when I eventually quit validating, I'm just going to exit back, and that's all good. It's fine, right? Now, the way EigenLayer is actually possible, the way that it works, is that you set your withdrawal address to a contract, right? So what you do is suppose this is your externally owned account, your regular Ethereum account. You've entered some ETH to the consensus layer. But when you did all of this, first you deployed a contract, which is an EigenLayer contract, an eigenpod, which you deploy. So for now, just think of it as this contract. And as you enter the 32 ETH into the queue, you're setting the withdrawal address as this newly created contract. Okay. So now the way, as far as the Ethereum system is concerned, if and when you eventually exit your validating services and exit your validators, that ETH is going to be sent to this contract, right? Now, okay, after you've deployed this eigenpod and you've set your withdrawal address to this contract, to the eigenpod, you'll then probably register some AVSs, some of these EigenLayer services that you want to do work for, right? So maybe you want to provide services to the EigenDA and earn some rewards for doing that, right? You're basically, when you're registering this EigenDA as an AVS on your contract, you're giving permission for this contract to like you're giving permission over to the EigenDA system, to some contract that is kind of controlled by and serving the EigenDA. And that contract is going to have the ability to send a transaction to your EigenPod, updating it with a /event, right? So what that means is that if you are, you go through this process, you register EigenDA as this AVS that you want to willingly do services for. Then if you cheat and you do some slashable offense, this system is going to send a message saying, slash this pod, your EigenPod, 1 ETH for a specific violation, and it's going to provide like a proof or whatever of that violation. This contract then, your EigenPod is going to have this like a note saying -1 ETH. And then maybe you do another violation and you get slashed 3 ETH. And so at this point, this contract hasn't really done anything substantial to you in a sense, because your ETH is still in this consensus layer. Ethereum doesn't really have any idea what's happened. It still sees that you have, in this case, 64 ETH, and you haven't been slashed from Ethereum, right? So it has no idea about this. But here's where EigenLayer actually has some effect, is that when you exit from your validating services, you're going to send this 64 ETH has to go to this contract, because that's how you set it up. You can't change this now. And when this ETH gets sent to the contract now has this message saying the user can only withdraw 60 ETH, right? Minus the 4 they've been slashed. So they can only withdraw what remains. So in effect, this contract has slashed you as a result of your activities on this totally separate service, which has some corresponding contract, which then sent these messages. But you've effectively been slashed, right? So, and of course, because this contract has the power, like because your money is going to be sent, your ETH is going to be sent to this contract, and it has this kind of power over that ETH, you're effectively, as soon as these messages go to your contract and apply this note of withholding and basically burning some of that ETH, effectively you have been slashed. Like that ETH is kind of gone, right? As far as you're concerned, it's gone. So basically, that's how it works at a fairly high level, is you set this contract as your withdrawal address, and that contract, you give a certain amount of power to it, and therefore it can slash you. And so these various services then have the power to slash some of your staked ETH. Okay, so to recap really quickly, our 4 paradigms are, first of all, Bitcoin, a simple ledger secured by a cryptoeconomic capital, not a lot of capital efficiency because our ledger does very little and it doesn't run super fast. Next paradigm is Ethereum. We have essentially, in a certain sense, an infinite expansion of the capability of the ledger, of the thing which is secured by our cryptoeconomic capital, because we now have a fully Turing-complete programming language which can essentially do anything in a certain sense. So this is a huge increase in capital efficiency. This capital is now securing a lot of things, right? Then paradigm 3, we have rollups. Now what we're achieving is a huge scaling up of the amount of stuff, the throughput of this system, because we have our base system with its programming language, which is running at like 20 transactions per second, and we don't want to go too much faster. But then we're able to secure with this capital hundreds of Ethereums running in parallel on top of our core Ethereum system. We have hundreds of these L2s which can run on top and which inherit the security of the L1. So our capital is now being used much more efficiently, and we get this, hundreds of times multiplier on our efficiency, capital efficiency, in terms of the volume of stuff that we can do that we're enabling with that capital. And then finally, with EigenLayer Paradigm 4, we have this further evolution where our capital can now be reused. And not only can we secure all of this stuff running extremely quickly with all of our L2s and full Turing complete programming languages, we can also reuse that capital to secure systems which are completely outside of the tree of Ethereum, right? These systems which are completely different and do entirely new things, and there's really no limit that I can think of to what can be done here, except that these things need to have objective, like slashable events. So they do need to be objective in a certain sense. Now, maybe in a future video, I'll talk about the EigenLayer token, which is addressing this limitation I just mentioned, because they're attempting to handle these intersubjective work things. So with main basic EigenLayer, you're expanding this capability, this capital efficiency, to objective things. They still need to be, they can be outside of Ethereum and the layer 2s, but they still need to be these objective tasks for where we can like prove someone has committed an offense. But there's a huge range of things beyond that. Basically, all the rest of the things you can have computers and even people do would fall into this domain of like kind of subjective work, intersubjective work. So that is where the EigenLayer token comes in, which I may talk about in the future, but that's it for now. Thanks for watching. The next video may be on MEV. I also have a mega Ethereum diagram, which attempts to capture all of the major components of Ethereum. So I'll have a video on that soon. I also have a video on the Bitcoin security budget thing, which is basically ready to go, and several others. So watch out for those. And yeah, thanks for watching, and see you next time. Peace.